Hey everyone, welcome back after your exam. I probably have not graded it yet, so I'll probably grade it while I am currently on an airplane. I'm literally on an airplane right now, going somewhere I absolutely do not want to be, but I promised a kind of younger guy, he worked in the same research group as me, and I promised him I would do this. I forgot about it, doesn't matter. Have to go when I have to go. So I'm literally in the air the times I'm supposed to be in this class because, anyway. So thank you all for your patience. And let's see. So you just had an exam. I will get back to you on that. And we'll have a homework set, which will do some propagation of error stuff as well as you still got to do number 4. So we'll make that a problem set. And this is the last lecture on all this error analysis stuff, which I know probably hasn't been a lot of fun, but and I appreciate your honesty with me that you mentioned that this programming has been onerous. Okay, that I've been doing this a long time, so I don't relate too well, so it's good of you to tell me that. So again, I want to emphasize that it's not so much the learning of programming or really any of the technical knowledge that you get as a college student or even as a grad student for that matter. The impartation of technical knowledge also changes the way you think. That's really mostly what we're trying to do here. Technical knowledge can be Googled. Not when I was your age. Actually, even when I was your age, Google had just started right when I was your age. Technical knowledge can always be obtained. In fact, Einstein said he didn't. People said to him like, "Oh, you must remember all these numbers and constants," and he said, "I don't remember anything." He pointed to the books behind his back, his bookshelf. He's like, "I just go look up something I need from one of these books." But it's knowing to do that, right? So all this specific information that we impart to you is really designed more to get you to think better about the problems you face. Okay, so again, we're going to finish, it'll be quick today. We're going to finish all of this variance, covariance, error analysis, some of this MATLAB stuff will come to an end, although I think maybe we want to still find some ways to keep up the computer programming so that you don't just immediately forget what you've learned. For all the reasons I said ad nauseum. Then Thursday's lecture, which I will also film shortly, we're going to get back into the pure math, and we're going to do imaginary numbers, and then we're going to cover differential equations. This will bring you to the highest level that a chemist would ever get mathematically. Diffie-Qs that's an unpleasant subject, let me go ahead and tell you. You will not enjoy this. You probably never thought you were going to enjoy this, but if you did, you're wrong. So Diffie-Qs, the problem is that unlike calculus, where there's generally an algorithmic approach to solving integrals, with some exceptions like the ones that we did in class, like with the Gaussian integral. Imagine that the entire mathematical field is like that Gaussian integral that we did, where we had to square it and we had to use a Jacobian. Differential equations, you can never use the same approach twice to solve any differential equation, any different differential equation. And that sucks. You'll see. There are general strategies to solving differential equations based on the nature of the differential equation, but reality is that there is no algorithmic approach to doing that. So anyway, I'm getting ahead of myself. Let's talk about error analysis, and I want to bring up what I did last time, because I don't think I was very artful in my description. So here I have an example of what you're going to do in Chem lab, which again is the pressure versus time, and it's called the effusion experiment. What you do is you're going to see that a high molecular weight gas infuses slowly, so this is pressure versus time. It looks like a slow dynamic. And a low molecular weight gas infuses very quickly for kind of obvious reasons. And okay, now notice I've done, so this is one gas and this is another gas, and we're going to try to figure out whether they're really different from each other. As I mentioned before, what I'm going to talk about here is, do we want to analyze just 2 sets of data, or do we want to replicate the experiment Remember, 3 is the magic number. There's no error analysis unless there's 3 numbers. So I have 3 replicates. Now the data is composed of more than 3 data points. So each graph has more than 3 data points. Looks like 100, like on that fake data I sent you. And then I have 3 replicates. What I'm showing you is the best way to do an experiment in terms of error analysis. I have a lot of data points and I have 3 replicates. It doesn't get better than this, okay? But it's just really necessary. All right, so let's look at this data and let's do the fmin search. And so we're going to get a tau1 plus or minus sigma tau1. Here we're going to do an fmin search and we get a nice fit. We're going to get a tau4 plus or minus sigma tau4 plus or minus an error. So tau1, tau2, tau3, tau4, 5, 6. That's my scheme. Okay. So actually, what am I doing? Let's go ahead and do that. Tau2. We do a fit. Another fit. Notice that these are awfully fast. And I will have sigmas associated with that. Again, exactly the way that you know how to do. And so again, the point of this is to understand what is our optimal approach. What is our optimal approach in terms of the error analysis? And what I mean by that is, do I really need to do replicates or not? Okay. The reality is there's no algorithm for this. There's no set standard for when do you want to do error analysis by just variance covariance or versus replication. Okay, now in the case that we have here, it is clear that tau1 is probably short. This looks like a fast dynamic, and tau4 is quite long. This is probably a light gas, and that's a heavy gas. So if tau4 is greater than tau1, now you can imagine that, do they overlap? What tau1 plus sigma, tau4 minus sigma, do those numbers overlap each other? I can see from this data that they clearly won't, right? I mean, I think all that programming you've done, you've developed enough intuition that you can look at these data and you know that tau4 is bigger than tau1, and even if here I'll write that, I'll subtract the sigma, plus or minus sigma, but let's subtract it, and let's take tau1 and add its variance, and it would still be less than that. So again, this is the worst case scenario on tau1, this is the worst case scenario on tau4 in terms of their overlap, and they don't overlap. Now, can you say that this is different than this? The answer is handedly yes. You really don't need to do these replicas. Okay, but let's say you did. Let's say you did. What you would do is, so let's call this gas A and gas B. So tau of A would of course be the average of the data. That's because I'm averaging it like normal because of this. I'm assuming that there's like a top hat distribution of possible tau values. I'm sorry, actually, I guess it would be a bell curve. But anyway, so no funny distribution functions need to be integrated. This is just a standard average. And of course, you know that in the sigma, and I'm using a different notation, the sigma of the taus of gas A would of course be sigma tau1 over 3 squared plus sigma tau. I'm just talking off the top of my head. I'm hoping that I am not screwing this up. And you can see why, I hope you see why I'm doing this. This is just a sum with a multiplied by a constant, and that constant is 1/3. So I hope you remember that this is the proper formula. The geometric average geometric sum is how you do this. Okay, and then you do the same for tau B, and then you would compare them just like I did before. And again, handedly, gas A has a lower, has a shorter tau A than gas B, and it's tau B, it's lifetime tau B. And again, if you build this, so we did for gas A, then you do the same for gas B. This is the ultimate approach to error analysis. Great, but really unnecessary. You could have just taken one data set, again, because each data set has more than 3 numbers, and for the reasons I explained before, this approach is overkill. All right, now let's compare it to an approach that's not overkill. And I'm going to get to tell you a little bit about some instrumentation, because I haven't done enough of that. I know that, we've talked a little bit about the kind of things you do in Chem lab. And again, we've talked about error analysis, which is something I think it would be very wrong of me not to tell you about, even though it's not technically in your little textbook. Okay, so let me tell you about quantum yield. So quantum yield, it has a very fancy sounding name. It's very simple. This is if a photon is absorbed by a fluorescent dye or a quantum dot, what's the probability that it emits a photon? So this is like an energy transfer, energy like yield. So it absorbs a photon, fluorophores do that, and then you want them to emit a photon. The odds that they do so are not necessarily 100. I know in your mind you think like, oh, a dye absorbs and then it fluoresces. It may not. Every now and then, actually quite often, it'll just get hot as opposed to fluoresce. The quantum yield is it's the number of photons emitted divided by, I'll write that down, number of photons emitted versus number of photons absorbed. A good dye, and there are good dyes, that number is 1. That's great. So you're not going to have more than 1. That's ridiculous. Something that we would call a dye like the dye in my shirt. This is not fluorescent. It's still a dye, but it's not fluorescent, so the quantum yield would be 0. It's an absorptive dye versus a fluorescent dye. Those are not the same. Okay, now how do we measure this? It turns out that, I'll tell you what, I can tell you about how you measure the fluorescence quantum yield with a quantum dot. You have to use a UV vis and you have to use a fluorimeter. You have to have both. Okay, so let's do absorption. And let's look at wavelength. And wavelengths on almost any spectrometer go from 200 nanometers to 800 nanometers, where 400 to 600 is basically the visible. So 200 to 400 is UV, and 600 to 800, and for practical reasons the machine stops there, that's near infrared. All right, so anyway, that's just practical information. A fluorescent dye has an absorption that looks like this. For various reasons, they tend to look like this. And you'll learn a bit about this in Chem lab. A quantum dot has an absorption that tends to look like this. It's very different. It's more absorptive overall. So cool. All right, now here's the thing. The dye, we're going to measure the emission of the dye in a fluorimeter, and that will also be a function of wavelength, and it will emit, it looks like around 600 nanometers. That makes that red. Okay, so we're going to have to excite it at a certain wavelength, and so we'll excite it, say 500 nanometers, which is green, and then we're going to look from, say, 505 nanometers to 800 nanometers, however far the fluorimeter goes. They usually go to 800 nanometers. Happenstance is the same as the typical UV is. And we're going to measure the emission. Okay, so let's get that in here, 0. Okay, so a typical dye has an emission that oddly looks a lot like the absorption, just mirror image. Again, there's reasons for that, we'll learn about that in detail later. Okay, the quantum dot, and I'll dash that, is quite a bit different. It's much more symmetric and much more narrow. That's why people like this stuff. And, my research group studies this. There you go. Okay, now where's the quantum yield? All right, here's how you do the quantum yield. It turns out that the dye's quantum yield is known by, if you want to know how you do this, I'll let you know. It's a little complicated. There are ways to know the quantum yield of a material without a standard. That's really kind of a complicated thing. I can tell you about it some other time or in office hours. Regardless, somehow the quantum yield of the dye is known. Let's say it's 50%. All right. Now, what's happened here is both chromophores are excited at a common spot. So like right here. Okay. Notice that I excited the chromophores where they both absorb and they absorb the same amount. Now, if I'm a little bit left or right of that, I can take care of that mathematically, but hopefully you're kind of getting the point here. By exciting them at the same spot where they have the same absorption, they both absorb the same number of photons. Because the absorptivity, if that's like 0.1, means that it absorbs about 10% of all the photons that strike it. And they both absorb, if they have the same absorption, then they have the same number of photons absorbed. That's even if their concentrations are different. This has nothing to do with concentration. Now, the concentrations determine the absorption, that's true. But if they have the same absorption, regardless of what the actual concentration is, and the quantum dot concentration would typically be about 10, for them to look like this, the quantum dot concentration is about 10 times less than the dye, because quantum dots are very absorptive. Regardless, they have the exact same absorptivity at the excitation wavelength. So the excitation wavelength is in this graph, it's about here. Like I say, let's say that's 500 nanometers, and this is 505 nanometers, and you look to lower energy. You're not going to excite something at 500 nanometers and observe emission at 400 nanometers. That's crazy. That's energy going uphill. Sorry everyone, just a little funniness. We excite at the same spot, and now we have the recorded emission. Now here's the quantum yield measurement. The quantum yield measurement is to integrate the amount of fluorescence on a computer, obviously. We do that for the dye, and then we do that for the quantum dot. Okay, those are clearly not the same number. The quantum yield, I have to think about this, would be the intensity, the integrated intensity of the dye, of the other unknown, which is the quantum dot, versus the intensity of the dye times the QY of the standard, which again is the dye. We're assuming we know the dye quantity. Okay, and that's the quantum yield. That is the quantum yield of the QD, the unknown. Okay, so that's how that works. All right, so now you know a little bit more of experimental physical chemistry. The next thing to ask, though, is what's the error, right? So this is the point of this. I almost forgot myself. Okay, the error analysis would probably come in here, right? So I could look at, we could do some kind of examination of the noise of the error of an integral, and we have propagation of the error formulas. And of course, there is some noise in the spectrum. I didn't quite draw that, but I'm drawing it now. So there's some noise in the spectrum. But now, here's the thing. Here's the thing that probably strikes you. The error in the integrals is probably quite small. And even though we're doing a dividend here, we know how to propagate that error quite correctly. Regardless, the quantity yield we report plus the error in that quantum yield, the error is going to be shockingly low if we use this approach. This is stupid. we're going to get, say, a quantum yield of about, so the way I've drawn these, it looks like the areas are about the same. The quantum yield of the dye was 50%. They absorbed the same amount, so therefore the quantum yield of the dye is also 50%. It's the same as the dye because it has about the same emissive area. Okay, we calculate the error in that measurement using this data. We're going to get 50% plus or minus 0.0000001%. It is going to be absurdly small. Okay, now you see what I'm saying here? You're going to want to actually do replicates. This is one that you do replicates on data like this. So if you were to take this approach of just using one set of data to do the error analysis, you're going to look like a fool. You should know that you just prepare new solutions. You prepare new solutions, you take new spectra, and then you average the results, and then the error, so let me represent it this way. You're going to have 3 measurements, and you report the average of the 3 measurements in terms of the quantum yield, and then you take those 3 measurements, put them into MATLAB, and you say, hey MATLAB, what's the standard deviation of those 3 measurements, and that's how you do it. Okay, so that's another example. Let's do one more, and this is for that example I brought up before about cancer mice. Okay, so now let's say we have mice with cancer. Drug, no drug. Okay, and how long does the mouse survive? Okay. 2 months. I can't spell the thing for some reason. 1.5 months. Okay, now again, this is a scientific study and you have this data and you should intuitively know that you have a major problem. This is not publishable because I don't know whether this, yes, with the drug, the animal lived longer. 2 over 1.5 times longer. Does that really mean anything? I don't know. It might not. So you see my point. This is not publishable. Any publisher who got this is going to run into ethical standards that make this unpublishable. Obviously, you're going to do replicates, right? So you're going to have 2.5 months on another, and you're going to have 1.9 months on another animal, and this one lived 2 months, and another one lived 2.1 months, yada, yada, yada. Okay, so now you have data, so now you can calculate an average, plus or minus standard deviation of those 3 numbers. You have an average, plus or minus standard deviation. Okay, this is the bare minimum. This is the bare minimum that you need to have to begin to publish. Now, this is the point of today's lesson. So again, that should be obvious in light of all the stuff I've said. Here's today's lesson, which is you still need to have a better metric as to whether this is meaningful. You may say, okay, average minus the standard deviation, average plus the standard deviation, do those overlap? If they did, it sounds bad, but that's kind of half-assed. Sorry folks, back to task here. What we're going to do is you probably could intuitively imagine, to say that the average plus the standard deviation, average minus the standard deviation, if those overlap, makes the result meaningless or not, therefore it's meaningful. That's not a really robust, statistically robust way to decide whether the lengthening of time versus the shortening of time for the mouse with or cancer mouse with or without drug, is that meaningful? To do this, you use what's called students t-test. Okay, students t-test is the thing that you use to decide that. Okay, how does that work? So this is just a statistical paradigm for when you have a small number of replicated data to tell whether the differences between those data is different. All right, so this got started by Geezer, shouldn't say Geezer, anyway, this Geezer, sorry, where did I have this? He was William Gossett, 1908, worked for Guinness Brewery, and he needed to know whether the hops that came in to make the beer was different. He only had a few samples, so he would do tests on batch from a producer, another from another batch from a producer. He only had a small number of samples, that's all they would give him, and he had to know whether they were similar enough to go ahead with the brewing process. And he didn't want to just, half-ass it like this. So he developed this statistical test. He called himself student because he had to hide his identity because he couldn't tell people that he worked for Guinness. So that's where it gets its name. Okay, how does it work? Okay, I'm going to give you the algorithm, but I want you to know the algorithm exists. I cannot say that I really fully understand it myself, other than it's just based on statistics. Okay, so let's look at this. So let's call this tau 1 plus or minus sigma tau 1. And again, we have 3. We always have to have 3. Let's call this tau 2 for the mouse. And it has an associated error, sigma tau 2. And the student's t-test tells us whether they are truly the same, whether they are truly different or not likely different. Okay, so 1 is to calc the averages and plus or minus the sigmas. Okay, so we've done that. We know all about how to do that. Okay, number 2. Now, there's a couple of different forms of t-tests depending on the nature of your data. This is, don't even write this down, this is going to be a two-tailed t-test. Sorry everyone, weirdness, I'll explain some other time. Okay, so this is called a two-tailed t-test. Again, there's actually many types of t-tests. You have to know what is appropriate given the nature of your data. Okay, so we're using a two-tailed t-test, and we're going to calculate the pooled standard error. And that is this formula. Okay, let's call that SP2. And this is going to be N1 minus 1. N1 is the number of trials on data set 1. That's 3. That's the bare minimum. Okay, let's call it sigma tau 1, we know what that is, plus number of data points that were taken for the other, in this case the other mouse, the no-drug mouse. Maybe it's the other batch of hops. And again, I wish I knew where this formula comes from, other than it's just a function of statistics. Regardless, there you go. All right, number 3 is to calculate the t-value. And the t-value is based on the observables, the averages of the lifetime, in our case, of mouse 1, druggy mouse versus the control mouse. Obviously, the no-drug mouse is a control. Here is our pooled standard error. And then we've got, I know this looks like a kind of ridiculous function, but again, it's weird by my standards, and I do this for a living. Okay. All right, so that is a value that you calculate, and then we're going to make a comparison against a data table that is created based on statistical analyses. Okay, so there's a last step, which is step 4. There's degrees of freedom, which is, call it DF, and it is N1 plus N2 minus 2. Okay. And then 5, look at table. Student t-test tables can be Googled. They're very common. Again, this is actually very common used in biology. You will see this used in every biological paper that you would ever read. Okay, here's what they look like. They have degrees of freedom. Now, we're going to look at the degree of freedom for 4, right? Now, let's do this. Three cancer mice with drug, 3 cancer mice without drug, 6 minus 2 is 4. So we're going to look at the entry with 4. Then you have significance. This is on the top row, and I'm going to have to write all this out. And what you have is the T number. And so anyway, I'm just writing these down. And again, these don't mean a lot to me. But I did look up, I looked at the Wikipedia article on how to read this. It's not hard. While the absolute numbers are weird by my standards, I can still read off the table. Okay. Here's what happens. We get the T value. Let's say that I actually made the data set. We don't need to worry about that. Let's say I get a number of 2.2. Okay, that's between here. So let's just say it's 2.1. So it's basically closest to this entry. That's fair. The significance is 0.05. Now what that means is that you have a 95% certainty that they are different. So that's pretty good by my book. Remember that anything below 68%, remember that's 1 sigma in the Gaussian distribution. Anything below 68%, no one would accept. Anything above that, it's like, If you're getting 90%, people will start to believe you. If you hit 95%, that's very believable. What you actually do is just report the result and let people make their own decision. But again, if you're below 1 sigma, about 68%, that's that didn't happen. There's actually a way to do that. So again, I look at the t-value, I look at the significance, and so here's 90%, here's 85%, here's 80%, based on what our t-value is. Okay, now I noticed that I did say at one point, I said something that was kind of funky. I said, what's the probability that this is just happenstance? So in the data that I erased, cancer mouse with drug lived a little longer than the control. What is the odds that that is just happenstance? Now, we're going to do our t-test and report the result. But what are the odds that it's happenstance? That's called a p-value. Now, the p-value is the formula for that. Let's not worry about it. I just want you to know this stuff exists. T-tests are very important. P-values, I see those frequently too. I'm not actually sure how to calculate them. I do know it exists. If I need it, I'll Google it, and maybe I'll have it on the homework. All right. Now, the way this works is, I've actually covered this before. You may remember that. I was actually just talking about it. So here's a Bell distribution, and we know that if we have an observable, if our observed value is far out into the wings of a Gaussian distribution, then the result is meaningful. And if it's more on the interior, if it's in here, the result is not meaningful. So again, are we within 1 sigma, 2 sigma? We talked about this before. I won't repeat it again. Okay, now let's say you have a p-value. So you calculate the p-value, and let's say that you get a number like 1 times 10 to the minus 5. Therefore, that's good that it's low. It means that there is a 0.0001% that your result is not true by happenstance. So again, let's say this was the result of our mouse study. The mouse with drug lived longer. It had a good t-test. The p-value is 1 to the minus 5. It means that the odds that the cancer mouse lived longer with the drug, the odds that it lived longer with the drug, just rank. All right, so, sorry, I'll be done. All right, sorry folks, the way to interpret the p-value is that the odds that the mouse with drug lived longer but it wasn't meaningful. It seemed meaningful, but it just happened to not be meaningful. The odds are 0.001%. Now again, that's absurd. It's meaningful. That's how you want to interpret that. Now, the p-value is actually a function of the degrees of freedom. This is part of the calculation. Now, the way that works is what I've drawn here is a degree of freedom of about 5. Now, if you look up the degrees of freedom, let's say that you have less degrees of freedom. Now, what would it mean to have less degrees of freedom? It means you have less observables. Okay. Now, the way that a bell curve looks when you have less degrees of freedom is that it is wider. Now, you can imagine that if it's wider and you're out in the wings, that becomes less meaningful, right? Because there's more area. So, in the case of less degrees of freedom, you can see that while you're still out in the wings, the area is higher, which is bad. That means that you're actually closer to 1 sigma, which is bad. And that means your p-value goes up with less degrees. So again, less degrees of freedom means you have less replicates. It means that you have greater statistical uncertainty, and that means that your underlying bell curve is wider. And that means that wherever your observable is at is actually closer to a sigma deviation, which means that it's less meaningful. Okay, so with that, that's most of the hour filled, and so we'll just go ahead and stop there. Next class is going to be on complex numbers, and then the class after that, when I'm back, we will be doing diffie cubes. All right, so I'll see you all then.